Okay, so last class we were talking about, we started talking about some of the operating system's specific features. We talked about process management a little bit. Talked about what a computer kind of looks like on the inside in terms of sharing resources across these buses. Remind me, what's context switching? Okay, CPU switches from one process to another, and why is that bad? It's a necessary evil, right? But it's expensive. So you don't want to context switch too often, right? So you're kind of finding that nice middleman or something like that. So we want to think about I/O system calls and things like that, and when are they appropriate to put in our programs? And if you don't want to do I/O too often, you want to do I/O as often as you kind of have to, but you do want to think about I/O as being a very expensive thing. And one way we can kind of see this is, I've probably shown this in another class before. If you have a for loop that goes through and counts, well, here, have we seen like how much slower I/O is than? Have I shown that in a class before? How much slower I/O is than just counting? We have a for loop that goes through 1,000,000 times and just counts from 1 to 1,000,000, just an integer, and then you print it out once. That program runs almost instantaneously, right? But if you print out the current value of count each time through the loop, the program takes a long time to run. Way, way, way slower. Because every single time you go to print out the current value of count, it has to interrupt the CPU, context switch the process out, switch it over to the I/O wait queue, interface with the operating system for sending I/O out to the monitor, get back into line for the CPU, get back into the CPU, increment count, move on to the next step through the loop, then get interrupted again to do I/O. See how that's working? Expensive. Very expensive to do context switching. All right, so we kind of looked at what multiple scheduling for multiple CPUs might look like kind of at the top level. We care less about how the operating system works in this course. That's more of an operating systems subject. What we care about in here is the various system calls that we can use to leverage some of these abilities to have more than one thing happen at once, that it would make sense for those things to happen at the same time. Okay, and we'll look at some things like that. And we started talking about that last time. We were talking about HTTP. What's HTTP?
Transfer protocol.
Okay, Hypertext Transport Protocol. What's a protocol? It's a fancy name for a language. Protocols are a techie, geeky way to make you sound smarter, and it just means how two things talk to each other. So we're all using the English protocol right now. Okay, but we don't say that because that makes us feel weird. But try that for a week. Every single time you walk up, oh man, especially when you walk up to like a foreign person, we're not sure what language they might speak, like which protocol should we agree upon? Just see what looks you get.
English protocol class.
To see what, but English classes are different because they're more about writing and reading. You're not learning English. Like when you walk into do you have a Chinese language class here?
Yeah.
Yeah. You walk into the Chinese language class, you're agreeing to the Chinese protocol for that class, right? And your Greek protocol? Latin, are you Latin? Are you doing Latin yet? Hebrew. But you're in Greek 2? 3? Oh, you're done with Greek. That's good, right? You didn't like Greek.
I did Latin.
How was Latin?
Awesome.
Like awesome, like you liked it, or?
Awesome, like I wish I could have taken the second class.
ESL instead of ESL.
Yeah. You got to wonder. I think Latin is pretty important for probably medicine and things like that, because so many names of things and stuff are written in Latin. So to the average person, you look at it, it's like meaningless gibberish. But they probably really just kind of describe stuff in pretty simple terms if you know how to read Latin. I don't know. It just seems like one of those things that isn't that useful anymore. Yeah, but yeah. So for now on, for the next week, you're and you get extra credit if I see you doing this in public. Walk up to somebody, because usually when you walk up to another person, I walked into the classroom. I didn't ask you. I just assumed we were using the English protocol. For now on, every time you bump into somebody, we're going to do, oh, here, we'll connect this to computer science. Because, I mean, we still are connecting, even though it's kind of a funny conversation. How many of you have heard something called handshaking? Okay, handshaking. Okay, now, if you walk up to somebody and you shake their hand, it's more of like a polite gesture or something. How does handshaking relate to computer science?
Use the example of Wi-Fi where you try to connect to the Wi-Fi, to send
Okay. It's a very modern example. It's not a very cool example. Does anybody have a cooler example? Think old school. How many of you have ever used dial-up modems to connect to the internet? Okay, when you dial up to the internet, what happens?
A really loud
Right? How many of you have heard that noise before? Okay, most of us heard that noise before. How many of you just like heard it like in a museum or a YouTube video or something, but never actually like? How many of you never have actually established a dial-up connection? Has anybody in here never done a dial-up connection? So we're like right on that cusp, right? Yeah. All right, so that's handshaking. All that beeping and fuzzing and stuff like that is called handshaking. Now, because a modem is connecting to another modem, right? So you have what does a modem stand for? Modulator, demodulator. Goes both directions. And that's a fancy way of saying convert between digital and analog. All right, that's what a modem does, converts between digital and analog, which is actually kind of funny. How many of you have a cable modem at home? If you have cable internet, you have a cable modem at home? It's not actually a modem. What do you think they call it a modem? People associate modem with internet stuff, right? Because when you're going over the cable network, it's digital to digital. You know, your computer is a digital piece of equipment. What's coming over that coaxial cable is a digital signal. You don't really need to do any conversion in the middle. Maybe you need to do some decryption or something like that in the middle. But they call it modem because, I mean, you know, it's not really doing modem-y things. It just has kind of a naming, you know, has a semantic meaning to that word. You know, we had these modems and all that handshaking because, you know, really the handshaking wasn't even an important thing. It just was because of the cool noise. It made you feel like you were using your computers, right? Or is handshaking actually important? So when we had those old dial-up modems and we were doing the handshaking, what was the handshaking all about? What were they trying to figure out? So everybody in here said that they've done dial-up modems before, right? So you've done dial-up modems before. You know, what were you connecting with the dial-up modem? What were you connecting to, Alexis? Answer the question. When you used the dial-up modem, what were you connecting to? Terrible. Hey, who can give me an example of something they used the dial-up modem to connect to? If we connected to the internet with the dial-up modem, what kind of modem did we have? What speed modem? 56K? 33.6? 28.8? 14.4? 9600? 4800? 2400? We have no hand raises at that point. What's the oldest modem that we know about? You have 56K modem, right? I'm guessing for most of you it's 56K. Because, I mean, I think you're right at that transition period, right? Okay. The oldest modem I used was a 300 baud modem. What does the 300 baud modem do? See, baud's another one of those, you know, like in computer science, we have a lot of those. Well, not just computer science, technology in general. We have a lot of like funny sounding names that come from real places, but they really mean something simple, right? So baud is kind of a fancy way of saying bits per second. So 300 BPS modem, bits per second. Slow. Okay, that's very slow. If we think about that, so usually when we're downloading stuff, we think about how many K per second, or even more modernly today, maybe how many megabytes per second. Okay, so so let's think of to download at let's figure out how many megabytes per second a 300 baud modem produces. That's 300 divided by 8 takes us to bytes per second. So that's a 37.5 bytes per second network connection. Okay, then what? Divided by 1,024 gets us kilobytes. Divided by 1,024. Okay, so this is 0.00003576 megabytes per second modem. This is way before web pages. Come on. You want to download one picture with that? Go to lunch. Cover a couple of days. This is not working. So,
How weird you put the phone on it? You get the 300 baud when you put the phone on it?
oh, I know what you're talking about. Where you, it doesn't connect into the phone lines. You actually lay the phone on top of it and let it just kind of do it through airwaves. The 300 baud modem I was on did not do that, but those did exist. Yeah, in the very, very early days. Now, do you think back then the amount of data we were sending across the network was smaller than what we send across the network today? So that was pretty usable for. I mean, this predates the internet. This is when you're talking to things called BBSs. Have you heard of BBSs? What's BBS stand for? Hey, what are we, young people? I know. Dr. Locklear probably still remembers the abacus. I bet she does. Yeah, he's like 600-700 years old. I don't know. This stands for Bulletin Board System. All right, so bulletin board system. So this this is the precursor to the internet, where somebody would have a computer set up somewhere that had some software running on it, and they would have a kind of a shell type front end, almost like a DOS-y looking thing or a Unix looking thing that had maybe a menu system. Some of the stuff that we maybe wrote in Java, kind of in the first part of like 250 or something like that, where you have like a little menu and press 1 to do this, press 2 to do this. That was the program that when you connected to that server, you were talking to that. But the issue is that server is sitting there. Let's kind of draw a picture. So here's our BBS. And then on the back side of the BBS, well, it didn't have to be on the back side, but this one will be a small one. We'll say this guy had 6 modems. Most of them had more than this. So they would have to have, for this one, they'd have to have 6 separate landlines going to this thing with 6 modems on it. And each of these modems were connected into a serial port on this server. All right, so only 6 people could be remoted into this machine at once. Sometimes you try to connect to the BBS, you get a busy signal. All the modems were taken. You had to keep trying back until somebody finally hung up. We don't have that problem anymore, do we? So this used to be a problem. So maybe this is how you originally checked your email or played some games, things like that. Play some games, something like that. But regardless, you would dial into one of these modems from your house. So this is you over here. Let me get my. Oh, come on! I don't get a. I want my picture. Very
From last time.
I know. I can always get a skull though. Wait, I must be doing something wrong. Oh, wait, hold on. I might be. It's weird. No, whatever. That's our person. I don't want to do a skull. It's just morbid. And plus, you start using that too much, it's not funny. Right? You gotta. So we have one modem hooked to our computer. Actually, I would have put the modem here. And then what we would do is we would dial in. Well, at least Alexis finally joined class here.
I wasn't paying attention this whole time. I asked Corey one question.
You didn't know what question I asked.
Because I don't know anything about modems. I've never even learned about them.
Well, so why didn't you raise your hand when I asked how many people have never used a modem?
So I was asking you a question about work.
Dude, asking a question. I was asking a question during that question too.
It was the one time I asked a question. I was paying
Yes.
attention the rest of the time.
Except for all the other questions. All right, so we're at our computer. We use our modem. We connect over to the bulletin board service. So you have a phone number you dialed, right? Okay, so you dialed into a bank, and then it would route you to whichever modem was currently available, and you hear all the beeping, blah 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 blah, and that's called handshaking. What's going on? What are they doing?
Establishing a connection.
Okay,
Kind
but
of like saying who I am, who you are.
yeah, and
We
that's
can do
that's
that.
kind of how it would maybe work today. Back then, we were missing something pretty important.
Oh, weren't they like connecting to a certain computer? Because that's like how the 414 boys like got into that government computer, right?
Oh well, I mean, yeah. In this case, I dialed a phone number that led to this computer.
Yeah.
You know, so if you've ever seen the movie Hackers, you know, one of the scenes, the guy calls up, you know, some I think it was like a cable company or something like that, and talks to the security guard and say, "Can you read me the phone number on top of the modem there? I have a special report for Mr. Kawasaki," or something like that. And he, you know, so he had to get the phone number for it. Then he kind of hacked in or whatever. But yeah, so in this case, we're connecting to this BBS. So let's ask another question here. How many of you have heard of TCPIP? Seen that before? Okay, what does that stand for? Well, everybody should have seen it before, at least seen those letters next to each other. It's pretty much every single time you mess with your network card in Windows or something like that, or you know, there's the TCP/IP settings, right? It's one of the tabs. Okay, you might not know what the heck it's for, but it's one of those tabs, all right? Do you know what this stands for? It isn't, well, IP is an internet protocol. So this is a language. So this is Transport Control Protocol. This is a language for sending things over the internet. Now, more importantly, TCP, that language, has a goal. This is more, again, of a networking class concept, but it relates to what we're talking about in here. So this has a goal of ensuring data arrives at its destination. That means built into it is the ability to resend data if something got corrupt on the way there, that kind of stuff. Make sense? So it doesn't matter the details of how it works. That's a networking class thing. But for us, it's at the high level. It ensures that when you send something from here to here, it gets there eventually. And it will resend multiple times until it finally gets there. Okay, and it uses things like packets to break it into little chunks so that it doesn't have to resend the whole thing each time. If it fails, something gets corrupt, it's probably one or two packets that get corrupt, so it just resends those, and those guys are numbered, so it can kind of reassemble them in the right order on the other end, that kind of stuff. Now the issue here is that in the very, very, very early days of really pre-internet here, when we're talking to a bulletin board system, TCP, it wasn't a thing. It wasn't out yet. So when those modems are beeping at each other and stuff, like that, if you had a 56K modem or you had a 33,600 baud modem, that's the maximum speed that modem can send stuff. Right? 56K was actually similar to our modern internet connections where it was asynchronous. So the download speed was 56K, the upload speed was 33.6. Because it did some compression stuff to get the 56K, because telephone lines, analog lines, have quite a bit of noise on them. So all that beeping and stuff between this modem and this modem, that handshaking, is them agreeing upon the maximum speed they can send information back and forth without screwing up. Because they didn't have a backup plan. Make sense? So even if you had a 56K modem, you may not necessarily connect at 56K. In fact, very rarely did you get 56K. Kind of a 53K was considered a pretty good connection. You get sometimes 48. Sometimes you get 33.6. Usually 56K modems could at least do 33.6, but whatever. You were also at the mercy of how fast the modem on the other side was. If you had a 56K modem and you were connecting to a 28.8, the fastest you're connecting at is 28.8. Make sense? It can't feed you the data any faster. So all that handshaking, all that beeping and stuff like that was all about those two things agreeing upon how fast can we do things without screwing up. Make sense? Okay, so in this type of scenario, we're dealing with a very limited number of simultaneous users. Now, realistically today, any system has a limited number of simultaneous users because we're sharing resources, right? But would Google have survived if you can only have 6 people doing searches at once? No, it needs to be able to handle more than that. All right. So this is kind of getting back up to this idea of having things split across CPUs, doing more than one thing at the same time. All right, so I think we brought up the example last time of if one of you was doing a Google search and if all the rest of us had to wait in line and wait for their search to be done, that would make Google very inconvenient to use. We kind of expect that when we connect to Google, it's giving us full attention, right? All right, so how does it actually accomplish that? Let's see where we left off here. So last time we were kind of showing we talked about HTTP. We talked about the 4 functions HTTP provides: get, post, put, delete. We mostly use get and post rather. So when our web browser, which is the client for a web server, makes a request, so for instance, this case, it's a GET request. We're requesting register.php. Web server receives that request, checks its file system, finds that that file, says, what's his MIME type? His MIME type is PHP. I need to spit out HTML and JavaScript. That's what web browsers know how to deal with. So what do I need to do? I'm going to have to run this guy through some sort of preprocessor, maybe the PHP module, run that program, whose output I presume will be HTML and JavaScript. Then I'll spit the result back out to the web browser. That's what's happening there. Okay? Now, in our example here, though, we have one human, one web browser. In the real world, we have hundreds and hundreds and hundreds of humans and web browsers all connecting to the same web server. This might be Google's web server, right? So there's going to be many, 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 many thousands of people connected at the exact same time. Well, how does it handle that? How does this guy right here allow us to have even 2 people both request a file, whether it's the same file or not, from this guy at one time? How many of you can talk to 2 people at one time on let's say, a phone? And maybe some of you might say, I could do 2. Okay. How many can you get 10 at once? Okay. There's only so many, you can only juggle so many phone calls, right? Where it's a one-to-one type situation. Well, let's say, so sometimes teachers have to deal with this, especially after tests when people want to come and complain about every little grading thing. So what happens? You have these people lined up at your door. So person 1 shows up at the door. I clone myself. Send my clone over there to deal with that student. Now I'm prepared to wait for the next student. Next student walks up, clone myself. Send the clone over there to deal with that student. Now I'm sitting here ready for the next student. Okay? That's how web servers work. Okay? Web servers, and really any kind of server that has to serve more than one user, okay? They're listening, for the door knock. They're listening on something called a socket. So last time we mentioned this DOS and DDoS. What's the difference between these? So this is denial of service. This is distributed denial of service. So typically, we only think about them in terms of DDoS today, but we typically call it denial of service. But it's almost always distributed now that way because you can only open up so many outgoing connections from one source. So now you need lots and lots of sources that all try to open up an outgoing connection to the same center person that you're attacking. That's a distributed denial of service. All right. Now, when we open a connection, when one computer opens a connection over TCP/IP, see, historically, when we opened a connection, we were looking at this guy, we opened up a connection over a telephone line. We dialed the number. Beep, 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 beep. That's the connection. Is over an analog telephone. We're tethered between these 2 points using a copper wire. Is that how we work? Is that how we do it today? If we want to connect to Google, do we have a runner that goes out there and copper wire and passes the baton to Google, hooks it up? How does the internet work? Okay, so all sorts of different kinds of, we might have copper, we might have fiber optic stuff, might have coaxial stuff, maybe we have carrier pigeons, who knows? We got stuff, right? We got satellites, microwave stuff up in space where something beams up there, then beams down there to kind of jump continents and stuff like that, because kind of running a wire over the ocean or under the ocean is, not that it hasn't been done, but it's not real efficient when you can just spend $1 zillion and put something in space, right? How else can you real-time chat with people in England? Go through a satellite in space. So what's good enough for DirecTV isn't it good enough for FaceTime? So, in any case, we used to connect over a physical connection. You see some of these old movies when somebody makes a phone call where there wasn't even a number, right? They just pick up the thing. It's like, talk to the attendant there. It's like, yeah, I want to talk to Phil up the street. And what does the attendant do? It shows like the bull connects the wires, right? Here's the incoming connection. This is Mike. And I take the wire and I hook it over to Phil's house. And then Phil's phone rings and Phil picks it up and they have a direct connection that I wired them together, right? And they're talking to each other. But then we started having automatic switching, right? And it allowed them to go a little bit farther than just around town. Well, now you've told me that we don't connect to Google over a copper wire. We're probably going into space at some point there. So every single one of you has traveled to space. Well, some aspect of you into space. That's resume builder there. Astronaut. 1996 to present. Should do that. I bet you that. At the very least, that will get you an interview. It's like, look, this person is not qualified, but I gotta know. Says here you're an astronaut. Yeah, I've been using the internet for a while. Did you know in order to go across the pond, you got to go through a satellite? So what's replaced these physical wire connections today? I mean, obviously you mentioned we have all sorts of different mediums. So we don't know what roads we're traveling across when we connect from here to Google. Probably some fiber, probably some copper, probably some coaxial, probably some airwaves, microwaves, things like that. Okay? But we need some kind of data structure to kind of govern that connection. Something, like we need to be in some sort of like a vehicle, to get there, to kind of, establish our connection, kind of hold on there, right? The person who's kind of holding the two ends of the wire, and they're the conductor. They just shake a lot, right? Anybody know what it's called when we establish a connection over TCP/IP between two machines? What that tool is called? Socket. Yes, we have something called a socket. We have a socket connection. Okay, we actually have two different kinds of sockets. Anybody know the two different kinds of sockets? A lot of times gamers might know the second one. UDP, yeah. So we have TCP sockets and we have UDP sockets. Okay. Do you know what the difference is?
UDP doesn't care about whether it's actually received or not.
Yeah, so here's the deal. So TCP, we already kind of talked about that. TCP guarantees everything arrives. Okay. UDP doesn't. UDP doesn't. Now, on the surface, we might say, well, that's not good, right? But for certain applications, it's actually better. How many of you watch Netflix? Okay. Now, when you're watching Netflix, you're probably watching a show at, 60 frames a second. Just throw that out there, something like that. Probably the shows are actually transmitted in less than that, but let's just use that number. It doesn't break the example. So you're watching at 60 frames a second. So that means 60 pictures are showing up on your screen every 1 second. Now, if for some reason one of those pictures has a corrupt pixel in it, do you want your show to rewind a little bit? You want to pause, rewind? If 1/60th of a second you have one pixel that's off, or is your eye going to allow you to ignore that? Now you're going to have a problem if you have a whole lot of problems because basically you don't have a picture anymore. It's just garbled. Okay, but generally speaking, if you drop 1 frame or 2 frames, you're not going to notice the difference. You'd rather your show feel like it keeps going, right? So that's where UDP comes in. You're sending information, you're trusting the network that, really this isn't like a major, it's not like somebody has a giant electromagnet sitting on top of the wire between you and the Netflix people where, it's error prone, right? 98% of the packets that are being sent across here fail, okay, because there's a magnet in the middle. That's bad. It's bad for electrical stuff, okay? So, but generally we would say that our network connections are reliable, right? We accept that, hey, there's stuff that goes on, especially over Ethernet. What's Ethernet? This is the big fat phone cords that we use. Now mostly we're Wi-Fi now, wireless, but it's actually still the Ethernet protocol. Ethernet's a language? Okay, so we use the Ethernet protocol either over the airwaves or over kind of the fat telephone wire dealy thing, right? Okay, well, forget about all the little details of the Ethernet protocol. The Ethernet protocol is a bus-based protocol where all those little packets, all the people that are trying to communicate at the same time, they're just like you're all driving on the highway without any sort of traffic signals or anything. You're just all going. So sometimes there's accidents. Sometimes there's collisions where a packet smashes into another packet and it's a fender bender. And things get destroyed. And rather than fix the accident and say, oh, is everybody okay? We just destroy them and resend them. That's how TCPIP works. It's the high level, right? Okay, so we're kind of our own worst enemies. We keep coming up with new ways of sending stuff from point A to point B, but they all have their drawbacks. But generally speaking, Ethernet's been around for a while, right? Okay, we had some older things. We had token ring networks. That's before, I think, all of you. So I remember token ring from, I was probably maybe a freshman in college. We still had a token ring network somewhere on campus or something. But, in any case, they were different kinds of protocols for sending stuff between things. But Ethernet's been around for a while. Probably it's pretty reliable. We've decided this must be a decent solution to stuff. Now we focused more on how do we send stuff faster over Ethernet, right? Early days of Ethernet, it was 10 megabit per second. Then it was 100 megabit per second. Then it there was some 200, 300. Now it's like gigabit per second and then 10 gigabit per second. And, then you start throwing, now you start getting to well, actually before 10 gigabit per second, you get to the limitation of what copper can handle, right? That medium is no longer like, look, we can accurately send it, but you can't handle it. Okay, I used the example in a class earlier where you're like, you have the gallon of chocolate milk and you're pouring into the glass and the glass is already full, but you don't stop pouring. You're just bubbling out of there and then you have the straw in there and you're blowing the bubbles. You're pushing stuff into this pipe and the pipe can't handle it anymore. All right, so that's when we move to something like fiber, which has a broader, or coaxial, which also has a larger bandwidth, can send more stuff. So we can use that exact same protocol now over a medium that has, it's a bigger diameter. We can throw more stuff in there. All right. But we're still having to decide what things govern that stuff. When we connect from this point to this point, what's governing that connection? So we have this thing called a socket that we establish. So when we establish a socket, we're saying, I'm going to go from here. Now, do we still dial a phone number? Don't you all just have them? Don't you memorize all these phone numbers? You memorize all the phone numbers. How do you get to Google? Directly. Tell me about this.
You just say,
Have you seen somebody about this? Okay, so it's ultimately still hitting the Google service, right, behind the scenes. They've given you a convenience tool, right? They've given you a convenience tool, but you're still hitting Google. Now, when you sit down at a computer, even though most of our web browsers now have a convenience tool where you just type in what you're searching for in the URL and it automatically searches Google, right? But let's roll back at least a few years. If you want to go to Google's website, what do you type in? Yeah, go to google.com or www.google.com. When you type in www.google.com, what's the google.com part? It's called a domain name. What is a domain name? What's the purpose of that? What does that give you?
Easier to remember than the actual IP address or whatever.
Okay. Well, let's throw the other part here. What's the www part? Oh, it just stands for World Wide Web. Could we have said bob.google.com?
It's just a subdomain.
That's technically accurate. Probably the better way of thinking about this is a machine name. That's the name of a computer at Google headquarters. Realistically, their web server is probably a cluster of computers, a farm or something. So it's, the global name given to a warehouse known as www that handles all of Google's web traffic. Okay? So this is a single machine name. So this guy has a specific IP address at the Google domain. This guy is the IP address of the probably Google router. So there's a piece of equipment at Google, probably lots of pieces of equipment at Google. We're talking about a pretty big enterprise type place there. But if we dumb it down, there's a piece of equipment at Google that's their edge router. And when we type in google.com, that edge router has a phone number called an IP address, right? Instead of a phone number, it's an IP address, but it's still kind of a weirdy looking name, like 192, blah 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 blah. Now, if you're at home, if you have 192, 168, 1.12, 10.0.0.14, and then we'll do what can you tell me, for those of you who are kind of networking-y people, what can you tell me about those first two IP addresses?
They're private IP addresses, so it's just within 5 whatever.
Yeah, so
5
yeah, these guys are called non-routable IP addresses. So these are typically used inside something called a NAT, network address translation. So when you go to Best Buy and you buy one of those Linksys or D-Link routers or something like that, your wireless router, you put your cable modem into that guy. That guy creates a internal network in your house with non-routable IP addresses. Okay, what does that mean? Well, it means that if I'm in my house and I have a 192, 168, 112 IP address, you could have that same exact IP address in your house because there's lots of routers going around and we kind of don't have an infinite number of IP addresses. So the idea is that IP address only needs to be unique within my little world. Okay, the only guy in my house that has a truly unique IP address is my router, which is my client for my network address translation. So whenever I type in, any website or whatever, my router is making that request on my behalf. My router is the only guy who has the passport to the internet with a real IP address, and he says, okay, I know that you're the one who wants Google, so I'm going to go ahead and ask him. But I'm going to ask him because I'm only allowed to go out there. You have to stay in the house. So he's going to ask when he gets the response, he's going to pass it on to you. Okay, that's how those kind of network things work. All right, what about this guy down here? What's this IP address kind of tell you? This is more geeky network trivia type stuff. IP addresses that start with a 169 indicate what? There is an error. Typically, it's a DHCP. You couldn't get an IP address. What is DHCP? Well, the P almost always stands for protocol, right? So some language, DHCP, Dynamic Host Control Protocol. Okay, fancy name for saying there's a server out there that will hand me a unique IP address that makes sure that I don't have any other IP address like somebody else on campus. So Concordia has a DHCP server, so when your laptop jumps on the Wi-Fi, it says, Hi, Wi-Fi. I need a unique address so I can do stuff. And then Concordia's DHCP server, looks up and sees, what IP addresses are currently available and hands you one. Generally speaking, like if in your dorm room, since you're on the same subnet, you will very often get the same IP address every single time because it's doing a little bit of cheating to take some of the processing off of the DHCP server. It's noticing your, well, here, we'll just keep going down the path here just a little bit. So how many of you have ever been banned on a video game? Okay. And they're banning your IP address, right? Okay, and you were at your house. And let's say you were, so how did you, now, even if you were in a network address translation situation, you were plugged into your router, the only unique IP address you had in your house was that of your router.
Right.
How did you get, if you wanted to still play that game, how could you get around that ban? Or you just stop playing that game? Maybe, but usually your cable modem will get the same IP address.
Can you can request a new one?
You can call the cable company and grovel and say, I want a new IP address, and maybe they'll give you one. You could also, see, the thing is your router is the guy that actually gets the real IP address. And the router has something called a MAC address, right? Or something called a MAC address. A MAC address is a unique hardware address. Most routers have a field on them where it allows you to spoof a MAC address. So instead of using your, so your router came with a MAC address, and that MAC address, is a unique thing across all hardware. And that MAC address, when a machine with that MAC address requests an IP address, it gets the same IP address typically from the DHCP server, because that's how they kind of make it efficient. Because typically, like a school like Concordia, our IP address space is probably bigger than our student population. So we can just kind of earmark an IP address for the same person each time. So what you can do if you get banned from a game, technically you're probably banning your IP address. They might be going farther than that, banning credit cards or something like that. So you have to use a different credit card to subscribe the next time. But I don't have any experience being banned from games. In any case, what you can do is you can look at the MAC address of like one of your computers, like your laptop. You can tell your router to spoof that address. You just paste that address in there. It's like a bunch of hexadecimal values. And then disconnect and reconnect your cable modem. You'll get a new IP address handed to your router because it thinks it's a new computer. Different MAC address. And you'll get it, and then you can go get banned again. So remember that for next time. All right, so you type in google.com at the on the web browser and you press enter. Is that good enough to get you to Google? We remember google.com. Okay, but we've mentioned IP addresses as being kind of the phone numbers of the internet. So now we have something called DNS, domain name service. This maps domain names to IP addresses. And this is a distributed system. Because do you think in any given second there's lots and lots and lots and lots and lots of people around the world that are doing searches for IP addresses, converting domain names to IP addresses? We said there was a lot of people using Google. There are a lot of people using all websites. It doesn't even have to be a website. It can be anything with an IP address. So DNS is done in layers. So we have a local DNS server here on campus, which hopefully has collected kind of most of the common stuff. So if we do a search for google.com, pretty good chance Concordia's DNS server is going to know the IP address of google.com. That's a common-y, lots of people are hitting that. So we're gonna have that one on file so we can map them directly there. But if Concordia's DNS server doesn't know about it, it's going to pass the buck to the next guy up. Say, hey, I didn't know this one. Do you know this one? Just keep going until you get to these top tier DNS servers that have all the information. It's like 5 or 6 of those or something like that. So that's what happens sometimes when your internet goes down. You think your internet is down, but you could actually sometimes get to a website via its direct IP address. So if you put in a text file somewhere what Google's domain IP address is or something like that, next time you think the internet's down, if you type into the browser the exact IP address rather than the domain name and you can get there, that means internet's not down, the DNS server's down. So sometimes you can try a different DNS server instead of the one that Concordia's DHCP server is handing to you, and you might be back up and running for at least temporarily or something like that. So some tricks you can play. Okay, so remember, Bible homework is due by midnight tonight. Maybe start looking at chapter 2 in the book. You know, kind of giving yourself some. You're trying to convert some of your knowledge of programming into the C world. Pretty soon here, we're going to be getting into Cloud 9 and start working with C programming at the command line. I will see everybody on Monday.